change that is required also begins to greatly increase. We can see from the left-hand graph that on the no attack scenario, the system is able to maintain 480 kilobits per second, and when it first starts up, there's a few parent changes. We can see that the number of black impulses, there's a fair number at the beginning of the system when nodes are trying to find good parents, and then occasionally throughout the lifetime of the system, a node will need to change parents in order to maintain its performance. However, when under attack, we can see that there are many parent changes to both good and bad nodes, and the number of attacks, or the malicious attack actually quadruples the number of adaptation changes in the network. So the network has become much more unstable and much more variable because of the introduction of malicious nodes. So there's been some prior work looking at robust adaptation. So the adaptivity can be exploited, has been shown in different systems such as TCP. Other work has looked at using trusted components in order to make sure that the adaptation decisions are correct, as well as using things like induced churn, but these systems often are high in cost and induce new components into the system. Other work has looked at selfish behavior, but this assumes that the nodes are simply selfish and not malicious. And finally, other defensive techniques have looked at structured overlay networks, which have a very different structure and can actually leverage this structure in order to maintain or make certain guarantees about who can be children and who can't be. And since we are in a completely unstructured network, we don't have any of these guarantees we can leverage. So the goal here is to create robust and adaptive components, and we want to prevent incorrect adaptations based on malicious data. So we want to actually use local decisions based on locally and partially observable global context. So there's actually two mechanisms we leverage, the first being the correlation of control plane and data plane information, and the second being context-sensitive outlier detection. We kind of think of these mechanisms as they won't be perfect and they won't stop every attack, but what they do is they raise the bar for the attacker to be much higher and much harder for them to actually attack the system and gain something out of it. So you can kind of think of it like the picture on the right-hand side is a castle. So a castle without a moat is hard to attack. A castle with a moat is slightly harder. And so our techniques are actually adding the moat around the castle in order to make the systems less vulnerable to malicious attack. So in order to use the control plane and data plane information to add robustness, that as I was mentioning before, each of the nodes periodically probes its peers for information. As it receives its information back from its peers, a node will construct a path graph as shown here at the bottom of the slide. And what it actually does is it uses this path graph in order to check the sanity of the data it is receiving back from its peers and neighbors. And so it can use this path graph to actually improve the decision performance by seeing if what is actually reported is correct. Now, for example, if we take the red node here as to be malicious, and if the red node were to report that it had no children to a node that constructed this path graph, it would actually be able to determine that this node is actually lying to it because it actually is able to see 2 children and 3 grandchildren as being part of this node subtree and avoid this node as a potential parent, and so thus potentially avoid a bad situation. So as I was saying, as each node probes peers for information, it will construct the path graph, and each node will construct it for each set of probe responses it receives, and if the inconsistencies occur, the node will be temporarily avoided as a parent. And we can see from the graph that while the system doesn't return to an optimal performance of 480 kbps, the improvement in bandwidth is nearly 200 kilobits per second for a very lightweight solution. We can see it went back up from 200 to nearly 400 kilobits per second, and this is with 30% malicious nodes. Not only does the performance of the system improve, the stability of the system also improves. We can see that when the system is working in a non-malicious scenario, there's a total of 411 parent changes. With no defense, this once again quadruples to about 1,600, and with our defense techniques, it drops back down to about 650, or a slight increase over the original without any defense and without any attack. So as a quick summary, we can see that the ability to adapt and change to network conditions and to maintain performance is critical to these systems. Once again, these adaptation mechanisms are vulnerable to malicious attack, and our experiments demonstrate that our techniques improve the adaptation process and the overall stability of the system while limiting the effects of malicious node, and also while incurring very little overhead on the actual system and not requiring any additional components. So finally, we'll actually look at using some of these components in peer-to-peer systems. So we actually look at using a robust virtual coordinate system, so robust network awareness in the core DHT. The core DHT is basically an efficient key value store. So each value that is placed into the core system is given a key, and you can search for the items based on this key, and then the item will be returned. So each node is given an identifier and a subset of values and is placed into a ring. So for example, here we can see a ring that has 256 identifiers. Each node is given a ring, and each node will maintain a subset of the data placed in the system. And each node in the system will maintain a predecessor, so the node that is before in the ring, the successor, the node after in the ring, the fingers, which can be thought of shortcuts across the ring, and finally a subset of values. So for example, if the node 100 here wanted to actually look up a value 230 in the system, it would simply send a message request across the structure and across the ring using its first finger table here, which points to 197. Then 197 would pass the message along to its successors in order to actually find the data value 230, which is also stored at the node that has the identifier 230. So in order to actually improve the performance of the core DHT, the finger nodes can be chosen at random. However, there are better choices than just random, as in that there are multiple choices for each finger node, and the finger node with the lowest latency to the corresponding node can be chosen. And so there are two ways to actually do this. The first is to probe all the finger nodes and check the responses, or to actually use the virtual coordinate system. So we can see on the right hand side we have our internet, and on top of that we have the Vivaldi system, which collects round-trip measurements from the internet, and finally we have Chord built on top of Vivaldi, which uses the virtual coordinates to actually choose the best finger nodes. And so we actually can show that a non-robust virtual coordinate system can lead to attacks on the system and lead to poor performance of the DHT. And so here we actually look at using a non-robust virtual coordinate system for latency estimation. And we can see that as the number of attackers increases, the lookup latency for the system begins to increase, and it increases with each percentage of malicious nodes added. And with 30% malicious nodes, an average lookup of the DHT takes approximately 50% longer when the attackers are present. One important thing to note is the fact that this attack actually causes no visible effects on the overlying system other than the degradation in the performance, which wouldn't normally typically be caught by the user. So all the other metrics of the system stay the same, the lookup rate stays the same, the success ratio stays the same. And so this attack would be very hard to defend against at an upper level and can only be defended against at the lower level system. So in order to actually add robustness to the virtual coordinate system, we discussed earlier, we used the outlier detection. And we can see here that the different detection techniques and the different percentage of malicious nodes, we can actually maintain the performance of the DHT or actually improve it because some of the fingers are actually better choices. And so using the robust coordinate system, we can see that the normalized lookup delay for 10% malicious nodes is 0.93, or 7% better than it was with using just the normal virtual coordinate system. And we can see that without that, the performance of the system actually suffers. So in summary, we can see that the malicious nodes can attack the lower level systems and detrimentally affect the upper level systems, and that these attacks have very little effect except to actually undermine the performance of the system. And finally, deploying a robust network awareness component is actually able to preserve the application performance. So in conclusion, peer-to-peer systems will continue to grow in importance. The open nature and the lack of security often make these protocols vulnerable to attack. And so here we looked at actually developing a framework of robust components which can be incorporated into current or new peer-to-peer systems in order to make them robust. These components include robust adaptation, network awareness, and responsiveness to identify threats. And we demonstrated the utility of these components in actual peer-to-peer systems. So are there any questions? Or did I just go over everyone's head?
David,
Mhm.
you mentioned that you implemented this in, was it cord DHT?
Right.
Do you think that the implementation would work equally well in other implementations of DHTs?
So I think it'll work. It actually, we've done it in other work and other systems, and does work equally well as the fact that core DHT, since it is a structured system that uses very strict constraints on who can be neighbors and who can't, and it really limits the neighbor set. It actually works better in other systems that have more freedom. We wanted to show that even in a system that has such guarantees, it can still be attacked, and that our techniques can still work. So it actually work better in unstructured systems than even the core system, but it works in other things like Kademlia and other DHTs. And so all those works, and so all these works have actually been deployed in real networks and across things like Planet Labs to actually run across large-scale systems with multiple hundreds of nodes. And so they actually do work across like a real actual working systems.
Would this approach work in a wireless mesh network? Has that approach been examined?
So which approach? Just
just the
using the components to build a more secure system.
Yes.
So it would work in pretty much any type of system in which a lot of systems are built on top of each other, and so you have one system, one subsystem which then are built on top of in order to make higher level applications. And so any application where you have that type of structure, these things will actually help. And so while the wireless mesh networks and wireless networks in general use different types of actual latency estimation systems, there are actually virtual coordinate systems and coordinate systems for wireless networks that work in very similar manners and can be used in similar manners. So yes, it's applicable to pretty much any type of networking. I mean, we focused in the work on wired networking, but a lot of the same techniques and principles would transfer to wireless with some augmentation. Any other questions?